Welcome to the 46th lecture of surface engineering. In the previous one, we discussed the process of physical vapor deposition, where we realized that we can always try to heat a material with reasonably low boiling temperature and high vapor pressure so that it goes into vapor state, and then obviously the vapor would like to come back to the ground state, which is the liquid or the solid state. So in the process, it actually will be looking for a colder substrate and get deposited onto the colder substrate, and that's how we can create few micrometer thick layers, which we call thin films, on all kinds of materials, or not necessarily conducting materials, also non-conducting materials. The whole process was based on heating the species that we want to coat. There are applications where exposing material to such high temperature is not always desirable. In fact, we may require, particularly for semiconductor industry, we may require certain thin coatings to be developed which will not be exposed to any thermal activation at all, because that may damage the performance of the device. So in a situation like that, we adopt a special category of PVD, which we call sputtering. Now, sputtering is, in simple words, it's like you are, here is a process where you scoop the material from the surface, literally atom by atom, by way of shooting certain tiny little projectiles, and in the process those scooped out species or atoms, neutrals, will find their way onto to deposit onto a colder substrate, and that's the process of sputtering. So let's try and explain what exactly it is. So first is we have a chamber, we have an enclosed chamber which we can actually, we need to evacuate. So this is how we can pump down to very low pressure, let's say typically 10 raised to minus 6 millibar pressure. So after evacuation, so there's no oxygen, there's no other reactive gases inside, very low pressure. So now we actually place the target. So this is the target which from which we want to take out material. Let's say aluminium, or let's say maybe gold, or maybe carbon, or some other whatever is the desired material. So we place it over here, and then also we have a stage on which we have our material which is to be coated. So let's say this is the component that we want to coat. Now we create an electrical circuit such a way that the target is connected to the negative electrode, the cathode, and the component to be coated is connected, or is actually grounded, or can be considered to be in the positive side of the anode. So we usually pulse at very high rate, and when we pulse electrical current at very high rate, then during the pulse on time, there'll be so once we create a very high electrical bias inside the chamber, and we would have backfilled with certain amount of argon, or usually argon. So the argon gets ionized, and these ions actually get during the pulse on time, the positive pulse, they get very highly accelerated charge. They move at a very high velocity towards the negatively biased electrode, the cathode. So these are the argon ions which are now energized at a very high velocity, accelerated towards the cathode. And when they hit the cathode, here or wherever it is, they will be able to dislodge some of the atoms sitting onto the surface. Now we already studied that while discussing structure of solids, that the surface atoms are indeed at a relatively higher energy state than the atoms at the core, and they have a higher reactivity because they enjoy one degree of freedom compared to 1 degree of higher freedom than the atoms in the surface, because they have atoms missing above or below the surface. So these atoms, which when they are hit by these projectiles, individual projectiles of argon ions, some of them will actually experience an impact which will have an energy that can overcome the binding energy of the atom to the surface. So that would allow those few atoms to get detached from the surface, and so they get detached and then they come out. So when this process happens, then you actually see a number of such atoms from the target surface to come out, and these atoms actually now come and deposit onto the surface. So you first hit the surface with very high velocity, dislodge atoms, and these atoms now come and deposit onto the surface. So this transport can actually be pretty fast. In fact, if the PVD process takes, let's say, for a particular to deposit a particular thickness, if it takes an hour, here it can be done in few tenths of a minute. So it can be much faster. So the important part is that stepwise we first have to evacuate, then we create this high potential difference between the two electrodes. We feed in certain gas, which is usually argon, then we create the plasma, and now we are ready. So once we start pulsing at very high rate, then this process of removing atom by atom from the surface and then bringing them onto the wafer or the substrate to be deposited, then they create a very thin coating. So the process depends upon this ejection of atoms from the surface and this surface of the targets, so which is basically the source material, and the ejected atoms should come and sit on the substrate that we want to coat. So the ejected atoms, depending upon whether the projectile is hitting head on 90 degree directly normal or through a grazing angle, the kinetic energy of the ejected atom will greatly depend upon the energy with which the projectile had hit the surface and made it come out. So also it will depend upon the distance which it has to cover from the center to the periphery. So there could be a wide distribution of energy, and because of this wide distribution energy, there could be variation in thickness and even composition if it's a deposition, if the sputtering is from an alloy. Anyway, we need to create a vacuum and then backfill with an inert gas, usually argon. The interface, just like in the previous PVD process, this is also nothing but a PVD process, will also be a sharp. So you do create a sharp substrate deposit interface. The sputtered ions, which actually are only a fraction of the total number of ejected ions, will fly ballistically. In other words, they basically are dependent entirely upon the energy with which they are hit. So there is no thermal activation here, and they will move in straight lines and then impact the substrate or the chamber wall. So they can go and deposit on the chamber wall, or they can come and sit onto the substrate, whichever comes on their path of flight. But if the momentum is fairly high, then there could be a possibility of re-sputtering or re-emission of atoms from the substrate on which you are depositing. That means you are now re-sputtering atoms from the substrate surface, which you don't want. So you have to control the energy very carefully. And this high energy bombardment needs to be avoided. So at higher gas pressure, the ions can collide with the gas atoms, which is used as a moderator, and diffuse to the substrate. And when actually it hits and goes and sits inside, it actually can create a certain diffusion gradient, and in the process it can actually move inside the substrate and proceed up to a certain depth. The applications could be typically in semiconductor industry for various kinds of functional and decorational coating. It can be used for surface analysis and also has wide application in fusion plasma and space physics. So sputtering is used also to create a conducting coating or a non-conducting coating. So the applications can be multifaceted. But the most of the applications are in the semiconductor industry. Anyway, so so the typical process would require that, as I was saying, that this is the target, and these are the components on which you are depositing. Say, for example, silicon wafers. You may have an auxiliary heater here, which actually allows certain diffusion of the deposit and the substrate below, and in the process the sharp interface can be replaced with a fairly diffuse interface with a better bonding. So this argon plasma that you create it covers the entire distance in between except thin layers, some kind of a sheath which actually is devoid of very high density of these ions. Now the activation can be through direct current, so in that case you call it simply DC sputtering. You can also use high frequency inductively coupled radio frequency plasma, so it can be an RF sputtered induced sputtering. But the process remains the same, that you actually will have a sputtering target which will take the hits of these argon ions, will allow ejection of these species, neutral species, which go and sit on the surface of the cold substrate. So you can deposit metal, you can deposit plastics or ceramics. So that's the beauty. This is actually independent of the chemical nature of the coating that you want to deposit. So you use low pressure under a magnetic field to concentrate high energy ions. This is typically done in case of magnetron sputtering, where the magnetron, high flux magnets, actually confine the plasma in a smaller region, and in the process make the deposit more uniform and compositionally more correct. So the application wise, you actually use it either for creating a conducting layer or an insulating layer, or change the electrical resistance or the band gap. You can also use it for improving the corrosion resistance or wear resistance and so on. You can even create it just as a possible substitute for, let's say, galvanizing. You can create actually a cathodic or an anodic layer to prevent corrosion and oxidation, but very thin. And the other advantage is that you're not exposing to any aqueous bath, you're not subjecting to any high temperature, you're doing more or less at room temperature, and most importantly, you actually are able to maintain a very thin, precise layer. So this is the space I was talking about, which is called the dark space or the sheath. So you create a high density plasma all over. So if this is the anode or the positive side on which you have placed your substrates to be coated, let's say silicon wafers, and this is the target from which you are actually extracting ions or making the argon ions hit the surface and dislodge atoms from this, maybe aluminum, maybe carbon or any other material. So there will be a little region in between which will have very low density, and that's typically called the cathode dark space or sheath. The exact thickness and the location and the width of these region largely affects the overall coating thickness and the uniformity of the coating. One other thing is very important is that if you can look at this substrate here or this substrate here, they are tiny little, much smaller compared to the overall dimension of the plasma that you create, and this is how you actually can make sure that there is uniform coverage and no shadowing effect, no non-uniformity. So this plasma that we create is by ionizing a gas, which is usually argon, which I've already mentioned. The reason why we use argon is because it doesn't have any solubility in the materials that we are using, either as target or as the substrate. So like I was saying, that here is a situation where, let's say, this is an aluminum target and this is a silicon wafer, and we would like to create thin layers of aluminum in certain portions and not all over the surface. So where we don't want aluminum to get deposited, we'll cover it up with a mask, and rest of the regions will be exposed. So we shoot argon ion and it dislodges an neutral aluminum, and the aluminum arrives onto the surface like this. It can be a straight one like that, or it actually can come through certain circuitous path, some spiral path. But in the process, it actually can hit the atmosphere inside, or the atoms inside, and since we are dealing with plasma, so obviously we have these argon ions, cations, and also we have electrons. So they actually, the density of them actually will vastly control the rate and also the uniformity and the composition with which they arrive. So this can be controlled, like I was saying. One possibility is that you confine the plasma by way of applying high flux, high power magnet, and you typically a magnetron, and then you call it a magnetron sputtering. Similarly, the frequencies of the sputtering can be changed from some normal level of using a normal electrical power supply to an RF coupled power supply, and accordingly there could be certain differences. So this arrival will create the overall geometry, or overall thickness and uniformity will govern that. So what is important is that this angle theta actually at which the species is arriving is important. So they can be uniform with isotropic arrival distribution, or they can be directed with anisotropic arrival distribution. So that means in certain cases I want normal deposition with certain area coverage, or I can make it an inclined or arrival at an angle, and there the deposition will be different, and that may be required in a situation like this. So in this kind of a situation, if you want uniform deposition coming from the top, then these trenches here, the opening being so small, may not be able to allow entry of sufficient number of atoms into the trenches, and in the process you get very poor coverage in the bottom of the trench. On the other hand, if you can create a directed deposition, then actually you actually do see that the deposit here could be wider or more uniform. So with the narrower angle of arrival, you can have a better bottom filling or flooding. With a wider angle of arrival, you can have poorer bottom filling. So this kind of geometry or consideration assumes very important, very high importance when these dimensions are extremely small. Now generally when you are talking about a cutting tool or a large manufacturing device, the dimensions are typically in millimeters, if not centimeters. But when you are talking about a semiconductor device, maybe some reflector or maybe some photovoltaic device or some sensor, there these dimensions could be typically micrometer or even less than a micrometer. So the arrival direction or the directionality of the flow of these atoms during sputtering assumes very high importance. So in that case, we may use either wider or shallower angle of deposition. And that's how we can make sure that we actually can create wider coverage here and not end up having incomplete coverage at the bottom of the trench like here. So depending on the features that we want to develop and the dimension of the features, we have to select the exact arrangements for deposition. So there could be various types of sputtering, like I was saying, that radio frequency coupled sputtering, RF sputtering, magnetron sputtering, confined, ion beam sputtering, where we actually use an ion beam, not just individual argon ions, but directed focused ion beam coming onto the target for sputtering. We can use, we can allow entry of reactive gases and then create some kind of a situation where we create an oxide or a nitride or some other reaction layer onto the surface. Similarly, deposition could be assisted by an ion beam. So we actually, where the ion beam is not a part of the same chamber, it is created elsewhere, and that ion beam can actually come and assist the deposition. We can create a separate activation source for creating very high target utilization for sputtering. Also, we can have a very high impulse using a magnetron sputtering unit to create a very high impulse for deposition. The deposition rate could be much higher in that case. So these are the various possibilities of sputtering. By and large, the process remains the same, that we actually create ions, create a plasma. We direct the plasma by way of negative pulses, electrical pulses, force them to hit the surface of the target, dislodge atoms, eject atoms from those targets, and those atoms will fly ballistically and then come onto the colder substrate and then deposit. And we actually can deposit multi-layers, or we can have multiple composition, or we need not actually use the same target. We can use multiple targets. For example, in situations like this, instead of having a single target covering the entire area, we can have multiple targets here, and we actually can use the pulses. Let's say this is 1, 2, 3. We can sequentially create pulsing between this or this or this, and in the process we can see deposition of 1, 2, 3 or A, B, C, and in certain sequences. So time to recapitulate. What we have discussed is a special type of PVD technique called sputtering, wherein we actually take the material to the vapor state not by thermal evaporation, but by ion-induced ejection, which is typically the process involving high velocity ions hitting the target and ejecting some of the atoms in the form of neutral atoms. So these atoms now fly and then come and sit, and that's how we create a deposit layer. The typical process parameters would be the distance, the density of the plasma we create, whether we are using any auxiliary heating process to heat the substrate during deposition. Then obviously the material that we use, its vapor pressure, melting temperature, vaporizing temperatures, and so on. Then we also have to understand that one of the biggest advantages is the fact that we don't necessarily this is not an electrolytic process, is not an electronic process, but it's a process where we are using certain discharge, and by way of creating a very large potential difference between two electrodes. So it can be used in special cases also for non-conducting materials. Even plastics can be coated by sputtering, provided we have created certain provisions of having electrodes implanted onto the substrate on which we want to coat. So this is useful that we actually can be, this is not just confined only to metals, but is useful to metals, ceramics, semiconductors, polymers, all kinds of engineering solids. So thank you very much.